In the previous video, we looked at interpreting distance time graphs. In this video, we're going to look at position time graphs. So unlike a distance time graph, a position time graph includes direction. So the direction could be north, south, east, west, for example. We could use positive or negative to indicate direction. But that's because position is a vector. So you'll remember a vector is magnitude and direction. Well, distance is a scalar. So it's just magnitude, no direction. So what does the slope mean on a position time graph? Well, let's think about this. We know slope is rise over run, and we know that the position, or the change in position, would be the rise. So the change in position, we can write it this way. Change, delta means change, and that's the symbol for position. Remember, this little arrow tells you it's a vector. So this is the change in position over time. And the change in position over time is equal to the velocity. The symbol for velocity is v with a little arrow over the top. So just like on the distance time graph, the slope of the line tells you the speed, on a position time graph, the slope of the line tells you the velocity. So if we have a constant positive slope, that means the object is traveling with uniform motion. A uniform motion, that just means that there's no change in velocity. So uniform motion means no change in velocity. And because it's positive, it's traveling with uniform motion in a positive direction. And if the slope is 0, that tells you the object is stationary. So the same as a distance time graph. 0 slope means the object is not moving. And a constant negative slope, well, just like a constant positive slope, it tells you it's traveling with uniform motion. But this time it's in a negative direction. Negative direction. Okay, let's take a look at an actual graph here and try to interpret it. So first of all, I noticed that in this graph, unlike the previous video, it can go down. So you can have a negative displacement. You can't have a negative distance. So when would the displacement be negative? Well, the displacement is the final position minus the initial position. Then the displacement would be negative if the initial position is greater than the final position. So in other words, when the initial position is greater than the final position, you'll get a negative displacement. So looking at this graph, when is velocity the greatest? Well, we said that the slope is the velocity. So where is the slope the steepest? Well, this looks pretty steep over here and here, but I think the steepest part is right in here, sort of between about 360 400 seconds. Okay, that is what I'm looking for there, is the steepest slope, because the slope is the velocity. When was the speed the greatest? Well, it would be the same, between 360 to 400 seconds. Right at the end. Now it's traveling backwards here, back towards the origin, but it's traveling very quickly here. It's covering the most distance in the shortest amount of time. It might be a good idea just to pause the video here and take a minute to describe, just to think about exactly what this object is doing. Okay, the next question is, when was the average velocity, or sorry, I should say what was the average velocity for the first 60 seconds? Okay, so 60 seconds would be right there. So the average velocity for that point, well, the rise is 150 meters north, and the run is 60 seconds. So 150 meters north. Remember, we have to put direction because this is position and it's a vector. And I think we get 2.5 meters per second north. And make sure you try this on your calculator as well. It's possible for me to make a mistake. D, what was the average speed for the entire trip? Okay, well, the entire trip, the average speed. Well, let's just think about this. This object is traveling 300 meters north and then 300 meters south, all the way back to the start, the origin. So 300 meters there, 300 meters back. The total distance is 600 meters. They traveled 600 meters in 400 seconds. So the average speed is 1.5 meters per second. Notice there's no direction because this is speed. And what was the average velocity for the entire trip? Well, pause the video and see if you can work this out by yourself. We know that velocity is the displacement, that is the change in position over time. Well, if the object went 300 meters one way and 300 meters back to the start, then its displacement is 0. Displacement equals 0 meters. Therefore, the average velocity is 0 meters per second. It might seem strange that the average velocity is 0 meters per second, but it's because the object ended up right back where it started. The displacement was 0. And finally, what was the instantaneous velocity at 380 seconds? Well, to do this, let's find 380 seconds. There it is. Right there. Now this is not exactly a straight line here. So what I would do is use a ruler and draw a tangent line to make a straight line. Now, if you don't understand that, go back and watch the video called Determining Instantaneous Speed. So with the tangent line we've drawn here, and it's not perfect, and the tangent line you draw might be a little bit different, but I want to pick two coordinates on this line that are easy for me to tell where the coordinates are. Looks like we could pick a point right here at about 250 meters north. That's an intersection. And another intersection right down here at 100 meters north. So if I just take this segment of the line, and you try to choose a segment as big as possible, but those are nice coordinates for me. So that means that the rise for that would be 150 meters north, and the run for that would be between 340 seconds and 380 seconds. So the run for that would be 40 seconds. So 150 divided by 40, I get 3.75 meters per second north. That's the instantaneous velocity at 380 seconds.